last speaker of this morning session is Dr. Qi. Let me give a brief introduction of Dr. Liu. Dr. Liu is currently an assistant professor in the Department of Physics, City University of Hong Kong. He obtained his PhD from Purdue University in 2014. Before joining CTU, he worked as a postdoctoral fellow at Argonne National Lab. His current research interests focus on the structure property studies of functional materials with multiple neutron and synchrotron-based techniques. His broad research activities include the design and the synthesis of novel energy storage materials, phase transition mechanisms, and neutron synchrotron physics. So let's welcome Dr. Liu for the talk about the studies on the cyclic stability of nickel-rich cathode in lithium batteries. Dr. Liu, please.
Okay, thank you, Bill, and I think somebody should let me to share my screen. Host, host has disabled my screen sharing.
Okay, let me see whether I can give you the permission.
Oh, it's okay now.
Oh, okay, okay.
Okay, so hello everyone, and thanks for coming. And first, I would like to thank Professor Huang's invitation, and thanks for Dr. Zhang Biao's kind introduction for me, and this special event about PolyU. Okay, and the title of my presentation today is about spontaneous stream buffer, so enable superior cycling stability in a single crystal nickel-rich cathode materials. Okay, first let me simply introduce myself. Okay, my name is Qi Liu, and I get my bachelor and master degree from Herein University. I go very fast because Dr. Zhang Biao just introduced me a few minutes ago. Okay, and now I'm an assistant professor in the Department of Physics at the City University of Hong Kong. My research is mainly focused on X-ray and neutron physics, and do something research like energy storage, like lithium-ion batteries and sodium-ion batteries, okay, and even flow batteries, and also do some research on the phase transition, like a phase transition behavior, and also do some research that in the synchrotron technicals development. So I'm also do some instrument development. Okay, so and also lithium batteries. I think that a lot of speakers introduce a lot, but I can also briefly introduce a little bit. So lithium-ion batteries has been widely used today, right? So, and when it's first introduced into market, it mainly used as in a portable electronics, like a in the electronics, for example, used in portable phones and laptop and a digital camera. And in the 2010, there'll be a great shift for application of lithium batteries. And that shift from the application in the portable electronics to the power batteries, like many use electrical vehicles. And I do believe that in the future, there'll be no more novel application will be used for lithium batteries, like used in the military and the smart grid, or even the aerospace. But anyway, for any time, the future direction of lithium batteries just try to pursue the high energy density, right, and high power and a long cycle life for any time. Okay, so the lithium batteries is pretty easy, especially like a working principle, right? Here, let me take a lithium iron phosphate and graphite lithium iron phosphate battery, for example. Okay, this is a lithium iron phosphate cathode. So during the charge, the lithium iron will get out of lithium iron phosphate and insert into graphite layers. And during discharge, the lithium ions will get back again into from the lithium from graphite and insert into the cathode materials. So this is completely reversible processes, and you have to know that normally the typical lithium batteries is composed of 4 different parts, like cathode and anode and the electrolyte and the separator. But normally is a cathode and anode that determine the power of the batteries. So normally we do believe the battery performance mainly determined by the cathode or anode, but the cathode and anode normally determined by the structure, right? Okay. Here I give you a very typical examples. Okay. Now, I think graphite. Currently graphite has been widely used as anode materials in the lithium-ion batteries. That graphite has a typical layer structure. This typical layer structure can be allowed the lithium ions get in and get out of the structure. That could be used for the lithium-ion battery. So graphite is a very, very good cathode materials, anode materials for lithium-ion batteries. Basically, the graphite still today dominate the anode materials for lithium batteries. Okay, amorphous carbon. Amorphous carbon, because not have a typical layer structure and can only absorb or deabsorb lithium ions. So the capacity is very low and the solubility is also very low. And diamond is another typical carbon structure, right? But this kind of materials cannot allow the lithium ions get in and get out of the structure because diamond is extremely stable. Okay, so for this kind of material cannot has any activity, so there will be no capacity, right? So the structure determine the performance, and the performance will be give a response to the structure. So structural regulation, it should be a very effective way for battery materials design for any time, right? Okay. And we know that for many years, we know that the structural regulation can be realized in different scales in order to improve the performance of lithium batteries. So for example, we can optimize the thickness of electrode and the amount of electrolyte, and we can also optimize the morphology and the size of particle, right? And sometimes in order to increase the conductivity of particles, we can do some coating, right? So all this could be regularized as a structural regulation in a micro scale. But however, if you want to further increase the performance of electrode, you have to go deeper, right? That means to a micro scale to do something in a lattice or in the structure. Okay, but in this level, that's due to a limited characterization technicals, it's not easy for understanding and control. Even go too deeper, okay? And okay, so let's normally the material issues in the solid electrode. Now when we go deeper, right, in the micro scale. So we have to the question 1. So what are the material issues in the solid electrode? Okay, so I think there'll be 4 issues, right? The first one should be the electron transport in the solid. And the second one should be ionic diffuse in a solid. And number 3 should be a solid electrolyte interface, right? And number 4 should be a structure and the volume change of a solid, the phase transition. So that'd be question 2. Why we need to investigate the structure change? We just try to manipulate the phase transition and to fast lithium ions and electron diffusion. Okay. This is typical, for example, this is typical in situ excited data from the lithium iron phosphate during the charge process. So take 200 plane, for example. So the red one is a lithium iron phosphate and the black one is iron phosphate. And during the charge process, the intensity of lithium iron phosphate continue decreased, and while the iron phosphate continue to increase. So this is a typical two-phase reaction, right? So that's why when the lithium iron phosphate has been first introduced to the commercial market, this kind of materials has been regularized, cannot be used as a fast charging materials. That's because the phase transition is a two-phase reaction. two-phase reaction is normally pretty slow. Okay, but finally, using the in situ activity, we found that when we significantly reduce the particle size of lithium iron phosphate, this kind of materials could be the phase transition behavior of lithium iron phosphate will be changed from a two-phase reaction to a solid solution reaction. So that's why lithium iron phosphate can still has a very high read capability. Okay. So that's why it's very important to investigate the structure change. Okay. And normally, in situ techniques provide a very powerful tool for structural dynamic characterizations. So we know that battery is very, very complex the system, right? The component like a anode and cathode electrolyte separator that with different materials properties, right? Is very, very complicated. So the in situ calculation is just very critical to understanding the battery performance and potential risk. For example, the ZENS can be help us to know the valence change, right? The XRD could be know the structural change, and PDF could help us to know about the local structure change and bonding, right? And TM could be look at the atom, right? So, and if you want, these powerful technicals could be studied what kind of batteries, okay? Normally we use like a pulse cell, okay? And give me a second. Oh, sorry. Okay, like a pulse cell and a coin cell, right? And also even could be used to study the commercial cell, like 1865 cells. These very, very big cells. That's because the synchrotron batteries, synchrotron X-rays is very powerful. It can even to penetrate the thick commercial batteries, and also could be used to study the flow batteries. Okay, and so in my research group and in our research group, we just have our own research approach. So before we try to study a materials, we first using the different technicals to study the structural dynamics. For example, like XRD for a long scale structure change, the PDL for local structure change, ZENS for valence change, right? And then we try to do some regulations in a micro scale level. And finally, we can improve the performance of batteries and improve the performance of batteries. This is our research approach. And then I will give you two typical examples about this kind of how this kind of approach could be used to study the materials. The first one is about high voltage lithium carboxide. Okay, high voltage lithium carboxide. So why high voltage lithium carboxide? Why? Okay, so lithium carboxide, I think everyone here should be very familiar about these materials because everyone here has a cell phone, right? The portable electronics, especially the smartphones, just using the lithium carboxide as a cathode materials. But the lithium carboxide has dominated the use of portable electronics. So now from this electrochemical data about these materials, we know that for this kind of materials, when we charge it to high voltage, for example, to 4.5 volt, right? We know that more lithium ions can be removed from the pristine ions from these materials. Okay. However, you will find actually in the industry, these materials can only extract about 140 or 160 milliampere hour per gram capacity from these materials. That's why. Why? The higher the capacity, but when we charge the lithium carboxide to high voltage, this material will be experienced a series of phase transition. The first one is water disorder transition right here. The water and disorder transition will be substantially lower the lithium iron diffusion. And when we try to charge higher, and the transition to H13 phase right here will be seriously stress the structure. Okay, so these two unexpected phase transitions will need the capacity fitting in the deep charge lithium carboxide. So that's why when the lithium carboxide has first introduced into a market, it has been significantly strictly limited to 4.2 volt. They just try to avoid these two kinds of phase transition. Okay, now, and we have studied a lot about these materials. We have studied a lot of materials, and we have also done an in situ XRD. And we actually the lithium carboxide normally when we study when we talk about when we discuss this project with other professors in the world, and they think the lithium carboxide should be very simple system. But actually, the lithium carboxide is very complicated, especially when it's charged to a higher capacity and to a higher voltage. Okay, so when the lithium carboxide charged to a higher voltage, it will be experiencing a series of phase transition. That would be 5. Okay, and once again, right here, say in right here, okay, the 4, number 4 right here. Okay, you'll find there'll be the peak split, right? So this phase transition just a water-disorder transition. That means the lithium oxide initially has a hexagonal O3 structure, but when it charge, when it's go to this part, it will be transferred to a monoclinic phase. Okay, once again, the water and disorder transition will be substantially near low lithium diffusion. And the transition to H13 phase will be seriously stress structure. Okay, we have not know the problem about lithium carboxide, right? So we have to solve this problem. Okay, so and this is a collaborative work with a Huawei company. Okay, here we just try to choose 2 dopants, try to surprise the phase transition and increase lithium ion diffusion and the structure stability of lithium carboxide by 2 dopant. One is alumina and one is natron. And the alumina right here, we just try to surprise the water disorder transition, try to stabilize the high voltage structure. And the natron right here, we just try to increase the lithium ion diffusion right here. Okay, and we found that finally, we found that all obtained product can show about 190 milliampere per gram, and the capacity retention could be as high as 96% for 100 cycles. Okay, so this is very good materials. Okay, that means we can extract about 190 milliampere per gram capacity from these materials, and also the stability is very good. Okay, now we get a very good data, right? We just try to know why this materials performance is so good, right? Okay, finally, and we get some. We have also can get some information from electrochemical data. Okay, so now this is a pristine LCO. Normally, the pristine LCO will be experienced 2 phase transition, the water and the disorder transition, and the transition to H13 phase, right? But when the alumina has been added into the materials, the doping of alumina can effectively suppress the phase transition at a high voltage range. Okay, so doping enantiomer can also increase the lithium ion diffusion coefficient, but I didn't mention right here. Okay, and we have also done some in situ XRD. Okay, now you will find this is charge and this discharge process. Okay, you'll find there'll be very clear phase. It seems there'll be no phase transition, right? Now you'll find the doping alumina can effectively suppress the phase transition at a high voltage range, and the doped also can experience a single phase solid solution reaction process. Okay, for example, this is a pristine also. Okay, this is a water disorder transition and transition to H13, but for our obtained materials, the phase transition behavior is very, very clear, okay? So there will be almost no phase transition, okay? Okay, this is a typical Y example, and but today I just try to talk about something about the single crystal nickel-rich cathode materials. And once again, so we know that the prospect of future EV industry depend on the development of high-energy lithium-ion batteries, especially why we need to study the NCM materials. The NCM materials has been, okay, we just talked about the lithium copper oxide, right? The lithium copper oxide has been mainly used in the portable electronics, but for the electrical vehicles, and we normally use NCM materials, okay? This is NCM materials. Okay, the NCM materials has already become the best choice for high energy lithium-ion batteries in the electrical vehicles. For example, the Tesla, okay, just using the NCM materials. So for many years, though thousands of papers about exploration of high energy cathode materials, yet few has been commercialized. Okay, so for example, only a few has been commercialized, like lithium copper oxide and NCM and lithium iron phosphate and spinel materials. Okay, now for NCM materials, increasing the nickel content in a composition can significantly increase the capacity. So for example, if we increase the nickel content to 8%, to the obtained NCM 811 could be has a capacity as high as 200. But this kind of nickel-rich materials suffered a seriously capacity decay during the charge and discharge. Okay. And there are many reasons for a capacity degradation of nickel-rich materials, but most of them are related to particle morphology. So normally, the commercialized nickel-rich NCM material has a polycrystalline particles, right? But this kind of morphology always has a large surface area. So the large surface area means there will be large contact within the electrolyte, okay? So as a result, there will be more surface side reactions, and finally, there will be need to green boundary fractures, and this is the main reason for capacity decay and NCM. On the other hand, the single crystal materials has a great potential because it has a reduced surface area. That means animated the green boundaries, right? But there were also some problems about these materials. The first one is how to realize the large scale synthesis of nickel-rich single crystal materials. Okay, and what kind of lithium intercalation mechanism in these materials? So this work just focuses on improving the cycling stability of nickel-rich single crystal materials and revealing the related lithium intercalation mechanism. Okay. First, and we have realized the large-scale synthesis of nickel-rich single crystals with a combined soldier and solid-state reaction. And the particle size is around 2 to 5 microns. So you'll find the particle distribution is very, very good. Okay. So and the composition about these materials is about 83% nickel. So we call it nickel 83. Okay. Single crystal nickel 83. Okay. Now this is materials. Okay. Now. And so in order to study these materials, we have also synthesized some nickel-rich polycrystalline particles by the almost exactly same ways, just with a little different, okay? And the particle size is also has been controlled to 2 to 5 microns. And this material has also been studied for the comparison. Okay, now, and first, use X-ray diffraction, right? And X-ray diffraction found that these two kind of materials has exactly the same hexagonal layer structure. So that means the morphology won't change the structure or not. Okay, want to change the structure or not. So the both of this material has a hexagonal layer structure. Okay, even and the local structure they'll be tightly different, very tightly different about these two materials. Okay. Okay, but the performance has shown we found that our single crystal nickel-rich materials show much better electrochemical performance in a pristine polycrystalline materials. For example, okay, the initial capacity, the both of materials could be reach an initial capacity about 200 milliampere per gram, but the capacity retention for our materials that when it to about 100 cycles, it could be still has a 96% capacity retention, and will be 93% for 200 cycles. So this electrochemical data has been validated at our Acknowledgement lab. Okay, so and but for the polycrystalline materials, the performance is not so good and it decayed very, very fast. And another important thing is that there will be no water decay for our materials, but our water decay for polycrystalline materials is very, very fast. Okay, now the capacity one more thing, but the capacity retention is much, much better. So why? There may be some reason for the good performance, right? So we just try to study these materials. First, we do some morphology study about after cycling. Okay, and for sure you will find this two kind of materials. This is polycrystalline and this is single crystalline, right? So you'll find the polycrystalline, it will be has a after 200 cycles there will be a boundary crackles and also the pulverization, right? Okay, now this for sure, that's because the polycrystalline material has a very large surface area, right? So there'll be much area contact with the electrolyte. But for single crystal, this is a very huge advantages about a single crystal materials that will be show much better morphological integrity. Okay. Okay, and we've also done some electrochemical performance like a GITD test and impedance test. Okay. This is just some normal electrochemical test. Okay, we know that the single crystal show a smaller impedance and the morphology integrity of cycled of these materials. Okay, and another reason, and this is a very interesting way when we try to study these materials, and we have used the in situ XRD to study these materials. Okay, we have found a very, very interesting phenomena. Okay. Especially for this single crystal materials. Okay, so this is a charge and this discharge process. This charge and discharge. Okay, I didn't put the polycrystalline 83 data right here. I just put a single crystal data right here. Okay, now you will find this is different between these two materials. Right here, you will find a peak split right here, right? Okay, so what is peak? Why the peak split right here? And we know that this material initially has the hexagonal structure, right? But when the lithium ions will be get out of the structure, we'll find a phase transition has been observed right here. This is a monoclinic stacking. That means there'll be phase transition right here. And another difference is that at a high voltage, in a high voltage for this kind of materials, the high voltage stacking is very, very complicated. Much more complicated in the polycrystalline structure. Okay. We just try to dig out more structural information from in situ XRD materials. Okay, so this is lattice parameter change for a single crystal materials. Okay, now, okay, H1 phase for a typical NCM materials, normally the phase transition will be transformed directly from H1 phase to H2 phase and to H2 phase. No, the monoclinic phase right here. Okay, but for materials, we find a monoclinic stacking right here. And even also at a high voltage, you will find the high voltage stacking is very complicated for these materials. This is very interesting. I have studied hundreds of different kind of enzyme materials. I never find this behavior in the polycrystalline materials before. Okay, so why there'll be? Of course, I don't know the reason, but I've just found this phenomena. Okay, that means the nickel-rich, the single crystal nickel-rich materials has a very unique the lithium intercalation kinetics in the single crystals, and it could be trigger intermediate monoclinic phase transition between H1 to H3 transition. Okay, and also has a in a high voltage stacking. Okay, high voltage stacking. Okay, so this two phase what are the zero of this two phase transition? Okay, now we know that from H1 phase to H2 phase, right? You will find if the phase transition from H1 phase to H2 phase, the lattice parameter change is huge, right? That means for this material, if it change from H1 phase to H2 phase directly, the phase transition is very, very huge. The lattice parameter change is very huge. The huge lattice parameter change just means the huge microstrain. Okay, so we do believe that these materials, so if there will be the immediately monoclinic phase between the H1 phase and 2 phase, the monoclinic phase could be regarded as a stream buffer between the H1 phase and H2 phase. Okay, so and we have also done an in situ PDF. The in situ and the in situ PDF is very, very. We didn't get too much information from the local structure change. That means we just the local structure change just has exactly the same as the XRD diffraction change. Okay. Okay. Oh, sorry. So now we also found that the first two peaks lying below the 3.0 intron right here, that could be also associated with transition metal oxygen and also the nearest transition metal and transition metal atom pairs. Okay, normally the first peak and become asymmetric doublet up until to 3.7 or 3.9 volt. So, and this means that this just a regular, okay, octahedral, okay, that be distorted in the voltage. Okay, so that means this just further confirmed the phase transition from the horizontal structure to a monoclinic structure. Okay, and this is how this kind of phase transition happened. Okay, in these materials. Okay, and these materials, once again, this kind of phase transition has never been found in a polycrystalline structure. When I studied the polycrystalline structure, has only been found in a single crystal structure. Okay, so we do believe that this kind of phase transition could be very useful for the capacity retention for these materials. Okay, okay. Now there will be only a few minutes left. Oh, finally, I get a summary about this part. And first, we have prepared a single crystal nickel-rich cathode materials and large scale synthesis. And we found like the mechanical cracks observed in the polycrystalline, the particles can be greatly animated in the single crystals. And importantly, we find a monoclinic phase between the H1 and H2, as well as a high voltage stacking. So, and we do believe that this two phase transition and could be, and this unique, the lithium intercalation dynamics in the single crystals could be enable a stream buffer to reduce grain boundary cracks. Okay, that's why, that's the main reason why single crystals can be, has a much higher the capacity retention in these materials. Okay, now finally, I would like to regularize. I would like to thanks my students, thank my group, and thanks for funding urgency. Okay, and thanks for your attention. Thank you.
Okay, so thank you very much, Professor Liu, for your very enlightening work in stabilizing the high capacity cathode. So now may have time for one or more short questions from the audience.
Okay, Dr. Liu, I have a question, a short question.
Okay.
So actually, I still don't understand why the monoclinic phase is missing in the polycrystalline cathode. You observed this monoclinic phase, right, in the single crystal sample, but why it is missing in the polycrystalline sample?
Actually, I never find this kind. Normally, okay, Professor Huang, thanks for good questions. So your question is like why I didn't find this kind of phase transition in the polycrystalline materials. Is that right?
Yeah. Yeah.
Okay. Actually, I have just told about the two projects right here. One is about lithium carboxide, and one is about the NCM materials, right? So monoclinic phase transition is very common in the lithium carboxide, right? Lithium carboxide. That's because lithium carboxide, but when the nickel and the manganese has been doping or has been mixed with cobalt, so we can draw we can know that the monoclinic phase can be eliminated, right? So so normally okay, maybe talking this way, nickel and manganese can help the cobalt to animate the water-disorder transition. That means monoclinic transition. So it's very strange for me to find this kind of phase transition in the single crystal materials. But actually, so that's why normally it cannot be found in the polycrystalline materials. Actually, I still currently I still working on this project to find the reason why this will happen in the single crystal materials. Okay.
But your single crystal nickel-rich sample has the same composition as compared to the polycrystalline one, right? The only difference
right.
is the size.
Yeah, the size and the composition. Yeah.
The composition should be same, right? I assume
right.
the composition.
That's right.
Yeah, so it's very strange. It's
very
strange.
It's very strange. Normally for NCM materials and the water-disorder transition is not very common in the NCM materials. That's because the nickel and manganese could be hyper cobalt to animate the water-disorder transition. Yeah.
Is it due to the if you have too small particle size and probably your diffraction may not have enough resolution to identify the different lattice parameter. You know what I mean? If for large single crystal, probably you can have more precise determination on the lattice parameter, and for smaller size, probably due to strain or other effect, then it's not easy to differentiate this difference in the lattice parameter.
No, I don't think so, because this is a high resolution and a high power synchrotron technicals. Okay. So it won't miss any tiny structure change. It won't miss any tiny structure change in the characterization. Yeah.
Okay, thank you very much.
Thanks for your question.
Hello, I have one question.
Yes, please.
Yeah.
Thank you for your wonderful presentation. I want to ask that we know that the synthesis of the single crystal need a high temperature than the polycrystal cathode. So, which will cause serious agglomeration. So, I want to know how to fix the.
Excuse me, teacher. I cannot hear you very clearly. So maybe I will.
Sorry. Can you hear me?
No. Okay.
I want to ask that we know that the single crystal cathode need a high synthesis temperature than the polycrystal. So which will causes serious agglomeration. Right.
Can you repeat your question? Not your question again. So it seems that I cannot hear your question very clearly.
Maybe I can repeat his question.
Okay, yeah.
He says to synthesize single crystal sample, you need a higher sintering temperature, and at a high temperature, those single crystal are likely to be agglomerated. Right. So, is that right?
Yeah, that's right. That's right. Yeah.
So,
right.
What is next?
Let's mean how way to avoid the agglomeration when we do a synthesis. Is that right?
Yeah, or how to handle this agglomeration.
Okay, so
how to remove the agglomeration.
Okay, I think I cannot tell too much detail about this part. Yeah. So this is a very good question. Good questions, and about a single, currently about a single crystal, the materials, and normally when the question is very good. When we try to synthesize, we have to raise the calcination temperature to the higher. Okay, so we have to avoid agglomeration, but we have our own technical to avoid this agglomeration, but I cannot tell too much about the details about this part. Or sorry about that. Yeah.
Okay, thank you for your reply.
Okay.
Okay, thank you very much. So since Professor Liu is in the CTU in Hong Kong, so you may initiate the collaboration with him separately. And so because we have already run out of time, so we thank Professor Liu again, and also the other speakers in this morning session. So thank you very much for the support, and also for the audience for your patience. And this will be the end of this morning session. In the afternoon, we're going to start at 2 p.m. and we're going to have another 5 speakers in the afternoon. So all of you are welcome.
Okay, thanks again. Thank you.
Thank you.
Thank you.
Okay.